All right, we are almost done with our definite integral problem. We spent a lot of time yesterday getting up to this point, but our definite integral, -1 to 2 of 4 minus x squared, by the definition, a limit. And at this point today, we'll see how we work with the limit, but the limit as the mesh approaches 0 for the summation of f of c sub I, which we calculated to be this, and then times delta x sub I. We allowed delta x to be the same for all of our intervals, so we just need the 3 over n to represent that. So now it's a matter of calculating this limit, which will involve a lot of algebra and then just a little bit of the calculus of finding the limit. The first thing we need to look at, we are dealing with a limit as the mesh approaches 0, but our function, our expression, is in terms of n. And I mentioned this in our previous discussion. As delta x approaches 0, that means n is going to be approaching what? Okay, n would be infinity. And to see that a little bit more, we say delta x is calculated by b minus a over n. And b minus a is going to be a fixed number, the length of the x interval, so a constant, and that constant over n, well, if n approaches infinity, some number divided by n will approach 0. So we can kind of work that back and forth. So the very first thing we can do is change our limit into n approaching infinity. And now the summation, actually, before we write the summation, at this point we have several different steps of algebra to do. It doesn't matter what order we do them in as long as we do the correct ones. Probably the easiest thing to look at now is this 3 over n is multiplied by the entire quantity here, and it is a constant in terms of our summation. There's no I in that expression, so when I is 1, that part's going to be 3 over n. When I is 2, that part's going to be 3 over n. So we can think about this as factoring that out of the summation. So we can say 3 over n and then times that summation. And I'm going to rewrite just slightly some of the forms of our fractions here. I'll make it a little bit easier to transition. Okay. Now, I guess we need to keep in mind we're taking the limit of this entire thing. Now we've got to figure out how can we represent this sum in terms of n. And that's going to be involving some summation properties and those summation formulas that we looked at yesterday. We'll rewrite it using a couple of different properties. First of all, the summation of 2 or 3 terms added or subtracted together, we can separate that into the summation of each individual term. So I guess we need lots of grouping symbols here. First one we can say is summation of 3 from I going from 1 to n plus summation of 6 over n times I I going from 1 to n, and then minus summation of 9 over n squared times I squared. Okay. And from here, we'll go ahead and use those summation formulas. We'll still have the 3 over n out in front of all of that, but the summation of a constant we can rewrite as what?
That constant, is it a multiply?
Yeah, that constant multiplied by n. We looked at an example where we had 3 plus 3 plus 3 plus 3 plus 3. 5 3's added together, well, that's just definition of multiplication. Well, here we're still looking at 3, but we're adding n number of them, so that creates a nice little formula there for that summation. Now this next one, kind of take it in two parts. The 6 over n, we can actually factor out of that one summation, just like we did the 3 over n here at the very beginning. So we'd have 6 over n times, well, we'd have the summation of I left. And what's the formula for the summation of I? Okay, n times the quantity n plus 1 all over 2. And then our last part, we've got 9 over n squared that we can factor out. And now we're looking at summation of I squared. And that one, again, the formula n times n plus 1 times 2n plus 1 all over 6. And then close that bracket. Almost ran out of room there. But this now is just a massive limit and lots of algebra to simplify it to where we can calculate this limit. So next up will be lots of doing the algebra, and we can go ahead and simplify a little bit on this page right here, and then we'll move on to the next page. Looking at this part, well, one very quick simplifying, n divided by n, those would cancel, and then 6 divided by 2, we'd be left with 3 there. And keep that in mind when we move to the next page. We'll have that for that part. Of course, the 3n we don't need to do anything with at the moment. This last term is going to be the most amount of work. Now, immediately we can take care of one of the n's. N up top will cancel with one of the n's here, but we still have an n in the denominator. The 9 over 6 we can reduce a little bit, 3 out of each of them. Okay, so keep all that in mind. We'll move to the top of the next page. So, well, lots more algebra to work through here. And again, mainly this part right here, we've got some things we can do. Multiplying our binomials together, we'll have 2n squared plus n plus 2n would give us 3n in the middle, and then the last would be plus 1. All of that's over 2, and then times the 3 over n out in front. Now, the rest of this, that had simplified to 3 times that quantity, so we can multiply the 3 through there. And then we still have the 3n as our first term. So, let's see. Let's go ahead and multiply this through and actually separate it into three different fractions. We can do that because of the pluses. We have 2n squared over 2 plus 3n over 2 plus 1 over 2, but all of that multiplied by negative 3 over n. So we'll separate it out and then simplify. Sometimes we try to do too much all at once, and that's where we make our mistakes. And then minus 3 over n times 1 over 2. Okay. And we'll go ahead and rewrite our limit then, combining our first part here, 3n plus 3n, and then plus 3, and now these last three terms dealing with that negative 3 over n multiplied. Let's see, that's a square there. First term, well, 2 over 2, n squared over n would cancel, leaving the minus 3 times n to the first. Then our next term, n's would cancel, and we'd have the constant 9 over 2. And then this last part, well, there's nothing that will cancel, but we'll combine it as 3 over 2n. And now a couple other things we could do, but one main last thing that we need to look at, multiply that 3 over n through the parentheses, through the brackets. We could also combine, we'll go ahead and combine those two. So 6n minus 3n times the 3 over n. The 3 minus 9 halves would be what? Okay, negative 3 halves. It would be 6 halves minus 9 halves. So minus the 3 over n times the negative 3 halves. Actually, no. It's positive 3 over n times the negative 3 halves. And then our very last term. Okay. So as we look at this now, once again we can simplify a little bit. N divided by n leaves us with 9. And then this next term we can combine into minus 9 over 2n. And this last one would be minus 9 over 2n squared. And we'll finish this out up on the next page. So finally we're down to some calculus. We got the algebra done. Lots and lots of little things. Be very careful with those operations. Applying the limit now as n approaches infinity. One thing we need to keep in mind here, the property we're going to be using a lot, if we have a constant in the numerator and an n or n to any power in the numerator, denominator, 1 over n as n approaches infinity, that's going to equal what? Okay, that's going to be 0. So as we apply that limit up here, that property up here, Well, the first one, the limit of a constant, is just that constant. But then we have 9 over 2n. We have the n in the denominator. That part goes to 0. And n squared in the denominator, that part will also go to 0. So this is going to equal 9. So from the very beginning, we started with this definite integral and working through the definition of the definite integral and all of the many, many steps, we get 9. Now, thankfully, here in a little bit, next week we'll start seeing some shortcuts so we don't have to take an hour to do one problem. But it is good to see how we do it the long way, why it ends up being what it is, and then nice to see those shortcuts.
So what is 9?
Question, what does that 9 represent? Well, the definite integral can represent a lot of different things. Remember, the definite integral is a mathematical operation. And in this case, the answer is 9. Just like 6 plus 3 equals 9, addition is a mathematical operation. But we see addition showing up in a lot of different places. Integration like this, one of the easiest illustrations is that this is the area under this curve from -1 to 2. And we actually started out this way, -1, 3. So one way to think of it, that value of 9, represents the area of this region. Okay. And later on, in the next several weeks, we're going to see many more applications of the definite integral. But that is one of many different ways to use that mathematical operation.